Hello everyone, welcome back to another remote sensing lecture video. And in this lecture video, I want to wrap up our discussion on accuracy assessment by talking about something called the Kappa statistic. Right, the Kappa statistic. So if you remember back to our previous video when we were talking about how the overall accuracy was very sensitive to differences in the number of observations in each class, and you could have some really big problems if one class dominated the number of observations, that the overall accuracy would be really sensitive to that class and that class alone. So an alternative measure sort of for the same idea of overall accuracy is this thing called the Kappa statistic. And so the Kappa statistic ranges from 0 to 1, and it's basically interpreted as the probability that your model is better than random chance. I want to repeat that, especially because my handwriting seems to be a little bad here. Right? The Kappa statistic is a value between 0 and 1, and it's the probability that your model is better than random chance. So if your Kappa is 0, right, you are no better than random chance. If your model is 1, then you are 100% better than random chance. Right, and the nice thing about Kappa is that Kappa handles that idea of differences in the number of observations in each class, right? So I'm going to make this as a red note here. Right, is that Kappa handles the issue of different numbers of observations in each class. Right, so that's sort of the benefit of Kappa. And because it handles issues of different numbers of observations in each class, Kappa is really the preferred metric for comparing different models. Right? If we had, say, a random forest model and a support vector machine model and a maximum likelihood model, and we wanted to compare those three models, assuming they had the same classes, right? Kappa statistic would really be the way to go about that, because it handles the differences of the number of observations in each class, and it can be determined as the probability that your model is better than random chance. So what I want to do is I want to look at two different error tables and compare how the kappas look between them. Okay, so these are two different error matrices. They have the same number of observations, right? 40 total. They have the same number of correctly classified pixels, right? 27. So our overall accuracy is the same, right? But what you'll notice here is that this one, right, the accuracy is distributed more evenly across the four classes, right? And each class has the same number of validation data. Versus this one, right? This has that classic issue where we have the majority of our observations occurring in one class, right? 24 compared to 7, 5, and 4, right? So the majority of this accuracy, right? In fact, the only reason this model is as good as it is because of the fact that the water class has so many more observations, right? Relative to the other three classes. So this is sort of the classic issue that we just talked about. And what I want to pay attention to here is this Kappa statistic, right here and right here. Right, I don't expect you to calculate Kappa. The calculation is a little bit more complicated, but just be aware that it does fall directly out of this error matrix. Right, we don't have to bring in any additional information. But what you can see here is that even though we have the same overall accuracy, right, the same number of observations, the fact that they're distributed differently among the classes has a drastic impact on the kappa, right? So this kappa here, right, this 0.41 versus 0.57. Now, neither one of these models are particularly good, and that has a lot to do with the sample size, right? We only have 10 observations in each class. That's not a lot. So you have some issues with sample size here. But again, right, just shifting them from being mostly in one class to being distributed amongst all the classes, right, has a much greater improvement on kappa relative to overall accuracy, which was the same in both cases. So hopefully this shows you why kappa is so important. And again, I want to reiterate, kappa goes between 0 and 1 and is the probability that a model is better than random chance. And it deals with that issue of having different numbers of observations, as you can see here, right? Same overall accuracy, different kappa. And the different kappa is because this one, right, the vast majority of that accuracy came from one class. So the kappa is actually lower than it is if you have the same overall accuracy distributed sort of evenly across the classes. So hopefully that makes sense. And as always, if you have any questions, please reach out. Thank you.